Okay, I'm going to walk you through lesson 5.3, but before I do, I want to go back to one problem. So if you have your guided notes, this is on page 100, I believe, or it might be slightly off if you have a different version. But it's the phone usage problem. That's the one I'd like to look at first. And so it's a typical problem where they give you some statistics of two different variables. And so we have one variable is about whether or not people have a landline telephone. So we're going to make a two-way table. We're doing part A here, making a two-way table. Two-way table just means you have two variables. So one of the variables is whether or not people have a landline phone or no landline phone. The other categorical variable is having cell phones or not. So people either have a cell phone or no cell phone. So it's just kind of yes or no for both. And our two-way table is just a 2x2 4-cell table. So now if we go back and look at the numbers, it said 60% of households had a landline. Well, 60% is going to be the total landline, the total of the landline row. And then they say that 89% have cell phones. Well, the cell phones is the first column, the way I did it. So 89% would be a total of the cell phone column. And then, of course, the 51%, the both is usually the kind of the linchpin of this whole thing. So 51% have both. That would be in the cell, the table cell of the intersection of landline and cell phone. And based on that, knowing that you have 100%, of course, total, or 1.0 total, we should be able to figure out all the other numbers. So if we just do a little arithmetic in our head, we can figure out that the top row will be 51 and 9%. The first column will be 51% and 38%. And then we know that 60 and 40 add up to 1, which gives us only 2% here, which gives us 11% here, which 89 plus 11 does give you 1. So there you go. We've done this all with percentages this time instead of counts, but it's still going to work nicely. So we made our two-way table. Check that off. Part B says the probability that a household has at least one of the two types of phones, at least one of the two types. All right, well, 51% had both. 9% had just a landline but not a cell, and then 38% had just a cell but no landline. So those are the three groups that represent at least one or possibly two. Basically, it's everything but the 2%. So the answer to that one should be 98%. So most people, 98% of people, have at least one of those two types of phones based on this table. Part C, find the probability they have neither. Well, neither would be the 2% that are under the no cell, and they're also under the no landline. That's the intersection of the no cell column and the no landline row. 2% of people don't have either type of phone. Once you have the table, you see these problems are really pretty easy. And then the last problem, part D, find the probability that the household has a cell phone only. Cell phone only. All right, so cell phone only would be where we have just cell phone and nothing else. So it would be under the cell phone column, but it would not be a landline. So the intersection of those two would be the 38%. So 38% would be the answer for that one. And there's more than one way to calculate that, but that would be the answer to that one. All right, so there you have one way to set up a two-way table in order to find probability answers. Now I just want to call your attention to another tool that we do have and that you might want to use. It's actually a pretty simple tool, one that you might have used in some other class somewhere, maybe not even in a math class. Does this look vaguely familiar to anybody? This is a Venn diagram. When you only have two variables and each variable is binary, in other words, there's only two outcomes, then we can use a Venn diagram. And one of the circles could be those that have a landline phone, and the other circle can be those that have a cell phone. Now the key is this can actually be difficult if you don't do this the right way. The key is to start with the middle 51%. 51% had both, they told us. Well, the both would be the overlap of the two intersecting circles. That's the area of this kind of geometric diagram where the 51% that have both phones would reside. It's in that overlapping area. Now we have to be a little careful when we go backwards, because going back to read this, remember it said 60% had a landline telephone. 60% have a landline telephone. That's the entire circle. The entire circle that's represented with landline is 60%. And remember, we've already accounted for 51%. So the area that's outside the 51% but still a landline would be 9%. The entire circle has to add up to 60%. And if you've already accounted for 51% of the 60, then there's only 9% left over. Similarly, when we go to the next category, 89% have cell phones. Well, 89% is the entire cell phone circle. And again, if 51% has already been accounted for, 51 out of the 89 has been accounted for, that leaves 38% in that area. That would represent what we answered before, remember? The 38%, they have a cell phone, but they do not have a landline because they're outside of the landline circle. So they would just be the cell phone only group, and that's the answer to part D. And then this area outside would be those that have neither a cell phone nor a landline phone, and there were 2%, you might remember. And so what you might be able to tell from this is the four numbers that end up being in a Venn diagram are the four numbers that are in your table. The four cells of the table, the inside table, I should say, the 51, 9, 38, and 2, those are the four areas of a Venn diagram. The three areas regarding the circles, and then the area outside the circles, which is 2%. So there's a connection there. And those are both of those methods are really good ways to depict a situation like this. So you can use either one or both, and there's going to be a third way here coming up that I'll show you, but those are both really good ways to do that. All right, so now we're getting into section 5.3, some new material here, and we're going to start with summarizing a two-way table. So once again, if you read carefully and put these counts, these are going to be counts, not percentages this time. And if you read carefully, the two variables are whether or not they won or lost the game. So that's one variable, the status of winning or losing. And then whether or not the fans got free tacos or no free tacos. This is our two-way table. Very simple again. This time, though, we're going to do counts. So now we have to go back and read carefully. It says that Diamondbacks won 41 of their 81 home games. So they won 41 of their 81 home games. And again, you have to read this carefully to realize we're talking only about the 81 home games, because the home team gives away the free tacos, not the visiting team. And so the win row would be 41, and the total of all the games is 81. There's 162 games in a baseball season, and half of them are played at home. The second piece of information that's important is the free tacos occurred in 30 of the 81 home games. So the free taco column would be 30 in that the bottom of that first column. And so 30 out of 81 got free tacos. And from here then we go one more. We have one more thing. In 26 of the games, it says, they gave away free tacos and they won. So that's always kind of the clincher. That would be the intersection of the free taco column and the win row. And that usually is enough information to fill out all the rest of the table. So you've got the total of the free, you got the total of the wins, you got the total, and then you got the overlap. So now we just go and subtract and do hopefully some easy arithmetic here to figure out what is in between all these numbers. So if we do that correctly, I believe we get these numbers. So the blue numbers are the ones that we were given, and then the red numbers are the ones that we had to figure out on our own. So there we go. We got our two-way table. Check that off. Now we have a couple questions to answer. First of all, what's the probability that they win or there are free tacos? Now we can think through this and do it. We can write a formula perhaps and do it. I would suggest that we could do it both ways. So how many of these numbers in the table are either in the W row or the free tacos column? And we don't, of course, want to count any games twice. So if we just highlight the wins would be these two numbers. And if we highlight the tacos, well, we don't want to highlight 26 again. We just want to highlight the 4. Those would be the three numbers that are either in the win row or in the free taco column. And we don't want to, of course, count the 26 twice. So it looks like there are 26 and 4, 30, 45. Looks like there's 45 out of 81. And we could get a decimal if we needed to there, but the probability can be written as a fraction. It can be written as a decimal. In this case, I think it's around 56%, something like that. All right, so if you are a formula person, and again, I'm not sure I would recommend a formula for this problem, but if you would want to do it with the formula, there's a formula that says the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So we could do this that way. The probability that they win a game is 41 out of 81. The probability that they get free tacos is 30 out of 81. But of course, if we just added those up, we've counted the 26 twice. So the 26 games that are both wins and free tacos are 26 out of 81. And you'll find out you'll get exactly the same answer if you want to go to the trouble of following a formula, which is totally fine. That's totally fine. You can do a formula, and you get the same answer either way. All right, so now we get to something brand new, something I'm not sure you've seen before. And it's a phrase using given that. We want to find the probability that they win given that they are giving away free tacos. This is what's called a conditional probability because we have to, first of all, focus our attention just on the free taco column. We're only interested in the free taco column. So we want to just focus on that first column of 26, 4, and 30. So given that, given that, you might notice is represented by a vertical segment. That's the symbol we're going to use for given that. So given that there's free tacos, in fact, let's just ask it this way. How many games did they give away free tacos? If you look up there, they gave away free tacos in 30 of the baseball games. So given that it's one of those 30 baseball games, how many of those 30 baseball games were wins by the Diamondbacks? Well, if you look at the table, it was 26. So it ends up being 26 out of 30, which is 0.867. And what you notice here is when you read this, the given that part ends up being the denominator. The part that you say first, like what's the probability of a win given that they got free tacos, becomes the numerator. So that little symbol in the middle there, that vertical symbol, you could almost consider that to be a fraction bar because the numerator comes from the first count and the denominator comes from the second count. And it becomes a fraction that you turn into a decimal or a percentage. So that would be a really easy way to figure out probabilities when you have a condition involved. You just look at the denominator first. Now let's flip it around. What's the probability that they would give away free tacos given that the Diamondbacks win the game? Well, how many games did they win? They won 41 games. So out of those 41 games, how many games did they give away free tacos? 26. So that's a different probability. It's like 63%. And, if you're a baseball reporter, You could say either one of those statements and be completely truthful, but notice how the probabilities look a little more dramatic. One of them looks a little more dramatic than the other one, like the 86% looks a little more dramatic. So if you want to be more dramatic in the writing of a baseball column, you could say, did you know that out of all the games they gave away free tacos, 87% of the time the Diamondbacks won the game? Versus saying, out of all the games the Diamondbacks won, 64% of the time they gave away free tacos. It's the same data and it's the same statistics, but you get a kind of a different, I guess it's a different flavor, different emotion comes out of that, even though it's the same data. But both of those are conditional probabilities. So what are conditional probabilities? Well, we just did two. So that's one way to answer it. What's a conditional probability? Well, both of those are probabilities calculated under an assumption of an event that's already happened. I think the book probably says that a lot more clearly and succinctly, but basically there's some sort of an assumption or a condition or something that's already happened, and it's out of that group that you focus your attention. So basically a conditional probability is not going to be out of 81. 81 is the total number of games that they won, but if there's a condition applied to it, then it's probably going to be out of the 41 wins or out of the 30 free taco nights. It's not going to be out of the total 81. So conditional probabilities are usually always about the numbers inside the table, not out of the total 81. Is there a formula? Well, yeah, there's a fancy formula. If you look on your formula sheet, the probability of event A, given that event B has already happened, can be calculated if you want to go to the trouble of using a formula of finding the probability of A and B and then dividing by the probability of B. Again, I can't think of a reason why you would ever use that formula unless maybe you didn't have a table and you didn't have the data sitting right in front of you. Maybe a formula would be nice if that's all they gave you is just, 2 out of these 3 pieces, and maybe you could figure out from there. But if you've got a table, there's no reason really to use this formula. It's great maybe for a test problem where there's no context, but it's not real helpful when you have a story because you can usually do it easier with a story. All right, and so now we come to the final way of depicting probability. And you may have seen this method in some other courses, perhaps, because it's kind of a very common thing to do to organize your thinking, and that's called a tree diagram. We have Shannon, who sometimes is late for school. Shannon hits the snooze bar 60% of the time on school days, and it turns out that if she does not hit the snooze bar, there's a 90% chance she makes it on time. But if she does hit the snooze bar, there's only a 70% chance that she makes it on time. And so we want to use a tree diagram to represent this situation. So the first thing we want to do is represent, it just happens that this is the first thing we want to represent. 60% of school days, something happens. She hits the snooze bar. 60% of the time she hits the snooze bar, and then the rest of the time she does not hit the snooze bar. Well, if there's only 2 things that can happen, of course, the other probability has to add up to 100%. So we can figure out that the other probability is 40%. So we had to figure that our own. We were given 60, but we know the other percent has to be the complement. And then it says if she doesn't hit the snooze bar, there's a 90% probability she makes it to class on time. So the other variable is making it to class on time or not. So this would be late, either on time or late. And so I'm reading this second little sentence here. If she does not hit the snooze bar, so I'm on this bottom branch, there's a 90% probability that she makes it to school on time. So that would be that branch, because it is, first of all, she does not hit the snooze button, and then second of all, she does make it on time, and that would be the depiction of that correctly. Now let's go to the very last sentence. If she does hit the snooze bar, there's a 70% probability she makes it to class on time. So if she does hit the snooze bar, then there is a 70% chance that she makes it on time. But of course, there is a little bit of a chance that she's late. And so if there's a 70% chance she makes it on time, that would automatically mean there's a 30% chance that she's late. And then down here, if there was a 90% chance that she makes it on time when she does not hit the snooze bar, that would make it a 10% chance that she's late. So this is a depiction of what they gave us. What we haven't yet figured out, though, is what's the probability she ultimately ends up right there? Two things have to happen. She has to first hit the snooze button. There's a 60% chance of that. And then she has to make it on time. What's the chance that she both hits the snooze button and she makes it on time? Well, you can invoke the AND rule for that, because that's what it is. When you say it out loud, she hit the snooze button and she made it on time. What's the probability of that happening? You simply multiply those two probabilities together. That's using the AND rule. So 0.6 times 0.7 is 0.42. So there's a 42% of the time that she'll hit the snooze button and make it to school on time. And we can go on down the line and do the same thing for all these other branches. We can figure out the probabilities of all four possibilities. So going down to the next one, what's the probability that she hits the snooze button but she does not make it on time? Well, that would be 60 times 30, 0.6 times 0.3, which is 18%. And then going on down the line, we always just multiply across. She does not hit the snooze button and she makes it on time. That's a multiplication problem again. 0.4 times 0.9 is 0.36. And then finally, the probability that she does not hit the snooze button and she's late to class, that's 0.4 times 0.10, which is 0.04. And if we've done this correctly, all of these should add up to 100%. So if we've done this correctly, these should add up to 1.0, and they do. Those add up to 1.0. And it turns out that if you would make a two-way table about whether she hits the snooze button or not, and whether she's late, well, we did it on time, I guess, on time or not. Guess what where these four numbers end up? These four numbers end up in the table just like they end up in the Venn diagram. So all of these methods that I've been showing you, whether it's a table or whether it's a Venn diagram or whether it's a tree diagram, we still have the four probabilities in the four cells of the table somewhere in the picture, whether it's a tree or a Venn or a table. So it's just another way to do it. However, the reason that we might want to do this, tree diagrams are good when there's like a first thing followed by a second thing. And in this case, she hits the snooze bar first, and then she may or may not be on time. So anytime there's a probability problem where there's maybe a first thing followed by a second thing, like there's an order to things, a lot of times a tree diagram is better. So now we should be able to answer any sort of question they might throw at us, like part B on a random day. What's the probability that she's late for class? Well, late for class would be two ways. She can be late two ways. She can be late after hitting the snooze button, or she can be late after not hitting the snooze button. And so there's two ways it can happen. It can happen this way, or it can happen this way, or means add in probability. So there's a 22% chance that she will be late to class overall. You can get that by just adding up those two branches. Now, here's one that's a little bit more complicated. Suppose she is late for school. What's the probability that she had hit the snooze button that morning? Well, it turns out that we just did the first part. How often is she late for school? Well, she's late for school 22% of the time. And out of that 22% of the time, how much of that 22% was after she hit the snooze button? Well, we got to go up to our table here. It was the 18%, wasn't it? It was the 18% of the 22% where she had hit the button. And so that would be like 9/11. And we could get that into a decimal if we wanted to. I don't have my calculator with me. But that would be the way you would do the probability. So out of the total lateness, which was 22%, she was, not 0.9 out of that 20, or 0.18 out of that 22% of the time she'd hit the snooze button. So we can get the probability there as well. All right. The general multiplication rule is on the formula sheet, so just know that it's there. You may use that at any time. The probability of A and B is always the probability of A times the probability of B, given that A has already happened. So this formula uses a conditional in there, and we now know what that means because we just went over that. So now maybe this formula would make sense. I already answered this. When's it better to use a tree diagram? When there is an order. When there is an order to the variables, the two variables. When Shannon gets up in the morning, first of all, she either hits the snooze or doesn't, and then second of all, she's either late or not late to class. So if there's an order to the variables, many times a tree diagram is a better way to do it. All right, one of the coolest problems ever is problems about drug testing or testing for diseases. There's a really, really good takeaway for everyday life. But I have another video that I do regarding breast cancer and mammograms that I'm going to have you watch instead of doing this one. It would also apply to COVID tests, which have a false positive and false negative rate that a lot of people don't really even know for sure what they are. But I'm going to do a separate video on that, so we're going to skip that for now. We're going to end with this problem, again, about the Diamondbacks. So remember, it was they either win a game or they lose a game, and they either get tacos or not tacos, free tacos or not. So I'm just copying down the numbers that we already had from the previous problem. But we're going to ask a different question this time. The question we're going to ask is whether or not these two variables are independent. Are these two variables independent? The variables are win-loss status and taco status. Are these two variables independent of each other? And without defining it, I want you to just think about it. To be independent, they don't have any effect on each other's probabilities. That's our definition in statistics. They don't have any effect on each other's occurrence of happening. Well, is that true? I mean, if you look at that data, does winning have anything to do with getting free tacos? Or does it not really matter whether you win or lose? Is there any difference in the taco rate? The chance that you get tacos based on whether you win or lose? I think it'd be pretty easy to figure out. I mean, what's the probability generally that you would get tacos anyway? What's the overall probability of getting tacos? Well, 30 times out of 81. That was the probability of getting free tacos. And 30 out of 81, I don't have that. 30 out of 81 is about 3/8, so I don't know, 35, 37% of the time, something like that. All right, well, let's see what the probability of getting tacos, given that they win the game. That should tell us whether winning has anything to do with getting free tacos or not. So out of the games they won, which were 41 games, 24 times out of those 41, they got free tacos. And I don't know why I didn't have my calculator handy here. This first one I said was around 37, I think, percent, somewhere around there. This one is more than half. I think you can tell that, right? That's more than half. So it's going to be 50, I don't know, 54 plus percent, something like that. Clearly, these are not independent. When the Diamondbacks won baseball games, they had a much higher chance of getting free tacos for their fans than when than the overall rate, or even just when they lost. So this would be a clear no. Are they independent? No. The probability of getting free tacos is much higher if they win, which, is common sense as well. If they win, they score more runs, and they would be a higher chance of getting free tacos. And you've got the work there that backs that up. And I wish I had my calculator handy, but I don't have that. So it's at least, 12 or 15%, it looks like, maybe higher than that. So how can you tell if the two events are independent? Well, basically, you have to make sure, you have to determine whether one event occurring has an effect on the other event's probability. So see if the occurrence of one event like winning has any effect on the probability of the other event. The other event's probability. Or I already said event, sorry. So if the occurrence of one event, like winning a game, has any effect on the probability of the other event, like getting free tacos, then we would say they're not independent. And that's what happened with the taco problem. All right, so there you go. I would like you to definitely do these two tables, fill out these two tables. This will give you and I both an idea of whether you understand the difference between mutually exclusive and independent. They want you to fill out that table under both those scenarios. And that's a really good problem to see if you've really got this idea of mutually exclusive versus independence. All right, so I know that was a little long, but I gave you the stuff that you need to know. And as always, if you have any questions, let me know. And I'll see you in class sometime in the future.